So in the last video, I talked about this first equation and how current can be used to make magnetic fields. So I had a wire that was wrapped in a coil, and as the current flows through the coil, it creates a magnetic field all aligned in the same direction. I'm going to use this second equation right here. I'm going to take a changing magnetic field and I'm going to create electric fields or electric currents this time. So just as a reminder here, right hand current pointing in the direction of the thumb, the fingers will point in the curling magnetic field direction. Here we have a changing magnetic field with your left hand pointing with your thumb, and your fingers will curl in the direction of the electric field. So just as a visual reminder of what that looks like, a positive charge moving to the right has magnetic fields wrapping in this direction. Here, with the north pole side of the magnet, electric fields are going to wrap around in the opposite direction, except for the south side of the magnet, because magnets must always have a north and south side. So the south side of the magnet is going to wrap around in the opposite direction when this magnet moves. Now let's consider what happens when this magnet moves towards a loop of wire. Well, because this wire has a bunch of positive charges in it, as this magnet moves towards it, these curling electric fields are going to push these positive charges in the wire. Now, the direction of these positive charges is going to go in the same direction as these electric fields. So current is going to flow in this direction. Now consider though what happens when you get to the back side of the magnet. So you have the north side and it goes through and it passes through. And now you're at the south side of the magnet. Once you're at the south side of the magnet, the electric fields will flip around in the opposite direction. So in the same way before, the current was flowing this way, now it's going to flip in the opposite direction. And so whenever you have this magnet that passes through the loop, you're going to get current flowing one way and then flipping around and flowing the opposite way. And you'll essentially get an alternating current. Now let's consider what happens when you have a bunch of loops. So instead of a single loop, you have a bunch of loops. And so we're back to this coil that we had before, which we conveniently figured out that it's just a bunch of loops connected together. So as this magnet falls down through the loop, what's going to happen? Well, electric fields are going to curl in this direction, and then the backside are going to curl in the opposite direction. If you were to align your thumb with this magnetic field, your fingers would point around in this direction. So then we can find out that current is going to flow in this direction and out through that side and in through this side of the wire. And then once the back side of the magnet will get through, the direction of this coil current is going to flip around. And now one thing I want to mention before we go on is the fact that energy is not going to be created in this process, because here's what happens. As this magnet falls down through the loop, current is going to flow around in this direction. But from the last video, we learned that when current flows, it creates its own magnetic field. And interestingly enough, because it's in the opposite direction, although this north pole is pointing down and creating currents, the currents themselves will actually point in the opposite direction of the north pole. And so what happens is that the north pole actually gets slowed down. So this north pole actually is getting pushed back up. And this should, in a way, make sense to you due to Newton's third law. If there are a bunch of positive charges in this wire, and the magnet right here pushes these positive charges around in a circle, well, there must be an equal and opposite reaction. So now these positive charges, as they move, are going to push back on the magnet. So the magnet pushes on these charges, but then these charges are going to push back and slow down the magnet. This idea is called Lenz's law, and it's the reason why conservation of energy is conserved. These electrons move, but they're going to slow down the magnet. They're going to take energy away from the magnet as they move. Now, what we can do to make an even more efficient motor is, instead of just taking a bar magnet and dropping it down through the loop and then having to pick it back up and bring it back to the top, what you can do is you just take the magnet and you're going to spin it. Well, what happens when it spins on this section of the turn? Well, on this section, it looks like the North Pole side of the magnet is getting closer and falling closer to the loop. But then on the back side, as it rotates the other way, now it seems like the south side of the magnet is approaching the loop. So the North Pole side is going to cause current to flow in this direction, out of the top side of the loop and in through the bottom side. And so that's indicated right here for the top part of this sine wave. And then when the south side of the magnet approaches the loop, you're going to get this bottom side of the alternating current. The current is going to flip in the opposite way. And so this is another reason why alternating current is used very often in electronics, because of the fact that it's so easy to create it. You just simply take a magnet, and by taking kinetic energy, you can directly translate it into electrical energy. Simply by spinning this magnet, it will create an alternating current. And so even at home, you can make that really simple. If you just have a lot of wire and you wrap it into a bunch of loops, and you take a magnet on the inside of this box right here and you spin it around. Well, that spinning magnetic field from the spinning magnet is going to cause electric current to flow, and it's going to light up this LED. And this is another graph just showing the same idea. You have this magnet, it's going to spin around, and those magnetic fields are going to go through the coil, and then they're going to constantly flip back and forth, and you're going to get an alternating current. Now, there's another way of making a motor. Rather than spinning a magnet, you can actually spin the wire itself and keep the north and south pole sides at the same point, and you'll actually get the same type of voltage curve. That might be strange because I told you before that it's moving magnets that will create electric fields, but here the magnets are stationary. This is sort of explained by another phenomenon called Lorentz force, which I'm not going to go into, but another way of thinking about it is from the perspective of the wire, it looks like the magnets are moving from the perspective or the reference frame of this loop, and due to special relativity, you can sort of imagine that this force is still going to exist.